Hello. So in this lecture or this short video, we are going to introduce monotone sequences, increasing and decreasing sequences, and prove what's called the monotone convergence theorem, which essentially characterizes when increasing or decreasing sequences converge. So what are increasing and decreasing sequences? Well, if we have x as a sequence of real numbers, we say that x is increasing if x1 is less than or equal to x2, so forth and so on. Basically, if xn is at most xn plus 1 for all natural numbers n. So this would be a monotone increasing sequence. Now, x is decreasing if the reverse of that inequality holds. So if x1 is greater than or equal to x2, dot, dot, dot. In general, if xn is greater than or equal to xn plus 1 for all natural numbers n. So then we would say that the sequence is monotone decreasing. Okay. So here are a few examples. We have 2, 4, 16, dot, 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 2 to the power n. This is obviously an increasing sequence, whereas we take the reciprocal of that and just do 1 over 2, 1 over 4, 1 over 16, dot, 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 1 over 2 to the power n. This is going to be a decreasing sequence. And here, Zn alternating between -1 and 1. This is obviously alternating for all terms, so it's neither increasing nor decreasing. So monotone sequences are very important in the study of real analysis, especially when we move on to looking at subsequences of sequences. And understanding when such sequences converge is going to be useful in proving a lot of theorems to come, right? So that's what the monotone convergence theorem does. It characterizes when these sequences converge. So what does it state? So I highlighted in yellow here the statement that most people would be familiar with, and that is a monotone sequence of real numbers converges if and only if it is bounded. Be sure to pay attention to that if and only if. So if and only if statements are characterizations of some properties. So this is a characterization of convergence of monotone sequences. What's more is that if a monotone sequence is bounded, it converges. If it's monotone increasing, it converges to the supremum of its terms. And if it's monotone decreasing, it converges to the infimum of those terms. So it actually tells us almost like a formula for finding the limit in that case. Okay, so let's go ahead and prove this. Now, it's a biconditional statement, so a monotone sequence of reals is convergent if and only if it's bounded. We proved in a previous lecture that, so I'll just write it out. If x is a convergent sequence, then it is bounded by a previous theorem. Right? We proved that all convergent sequences are bounded previously, so that's part of this result, right? So okay, so that's the easy direction because we already did the work to do that. If you haven't seen my previous lecture on this result, I should say by a previous theorem. If you have not seen that lecture, the way to show this is to assume that you have a convergent sequence, and then you can pick epsilon to be 1, use the definition of convergence, and then you show that the terms are indeed bounded. Okay. So that part of the theorem is done. What's left is for us to assume that we have a monotone sequence that is bounded and then show that it's convergent. So in order to do this, I'm going to focus on proving the case when it's bounded and increasing. And then the case for when it's bounded and decreasing is a very similar argument. So I'm really just going to focus heavily on the first equation here. So that is, so maybe conversely, suppose x equals to xn is bounded and increasing. Okay. So we're assuming that this is a bounded increasing sequence. Now, since it's bounded, we can just call that definition. So thus maybe there exists some real number, say m, so that xn is at most m for all natural numbers n. Okay. That's just the definition. Well, the actual definition of a sequence being bounded is an absolute value. The terms are no more than some constant real number. But in this case, it's an increasing sequence, so eventually it's going to be positive. So we can just ignore the absolute values in that case because it's increasing. Okay. So what does this imply? This implies that the set of these terms from the sequence, right? So xn such that n is some natural number, right? This set of the terms is non-empty and bounded above, right? If the sequence is bounded and this set is bounded above, then it's non-empty because we're assuming that the terms exist, right? So it's non-empty and bounded above. Now again, from a previous lecture, we know something about these types of sets. If you are non-empty and bounded above, the completeness property of R implies that the supremum of that set exists. So I'm going to go ahead and write that. So by the completeness property, the supremum of this set exists, and we're going to denote that by x star. So this exists. And it exists in R. It's some element of the real numbers. Okay? So since this is the supremum of that set of numbers, we know that it's the least upper bound, right? Meaning if we subtract any number off of any positive number from this number, that's no longer going to be an upper bound of that set, right? That's just by the definition of the supremum. So thus, we're going to say let epsilon, make sure that y'all can see that. So let epsilon be greater than 0. Okay. And observe, or maybe a note, x star minus epsilon is not an upper bound for that set. So probably going to run out of room here, but hopefully we can squeeze it in. But hopefully you also agree that since that's a positive number, if I subtract off a positive number from the supremum of that set, then it's no longer an upper bound. Now also, we're assuming that that sequence is increasing, right? So there's going to, if that's not an upper bound and the sequence is increasing, then we're going to have a big portion of that sequence that passes up that number. So what does this imply? So this implies some, I can fit it over here, I think. Some, yeah, that says some. K, it's just a natural number, some index, so that, well, x star minus epsilon is less than x sub k, right? But we know the sequence is monotone increasing, so that's at most xk plus 1, right? Which is at most dot, 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 the supremum, right? But the supremum is going to be strictly less than the supremum plus epsilon. Okay. So what does this imply? Every single term of the sequence above k is squeezed in between the supremum minus epsilon and the supremum plus epsilon. So this implies that x star minus epsilon is less than xn, which is less than x star plus epsilon, holds for all n greater than or equal to k. And we're almost there, right? Because what does this imply? This is the same thing as writing that minus epsilon is at most xn minus the supremum, which is at most epsilon. Which in turn implies that xn minus x star in absolute value is at most epsilon for all n greater than or equal to k. And that's the definition of convergence. We picked an arbitrary epsilon and we found a k so that the sequence minus this number is less than epsilon, or at most the distance from that to the x star is at most epsilon for any choice of epsilon. That shows convergence. Hence, the limit of xn does in fact equal x star, which is the supremum of the set of the terms of the sequence. Done. Now technically, we're not really done because we haven't proven the infimum version for the decreasing sequence that is bounded. But I would suggest that you try this on your own, mimicking this proof. So you could do it in two ways. You can say that it's monotone decreasing and bounded, which means that in absolute value, the terms of the sequence are bounded above by some n, which means that the sequence is, this collection of terms is bounded from below. Completeness property again implies that the infimum exists. And then follow a similar type of argument as we did here, just the inequalities are going to be in reverse directions. Now, An easier way to prove the second part here for the infimum case for decreasing sequences is to just take what we've proven for bounded increasing sequences and apply it to the decreasing case. For example, if yn is a bounded and decreasing sequence, then negative yn is a bounded increasing sequence, which we just proved converges. It converges to the supremum of the negative terms, which is equivalent to the infimum. So I think this is a good point to stop and allow you watching this video to try your hand at proving the second part here. Here's the template. You can either use what we've proven so far to prove the second part or do it from a similar argument as this.